Hello everyone, this is Priyanka from Edureka, and today we are going to discuss one very important topic in machine learning, that is regularization. So let's have a look at our today's agenda. We will cover the need for regularization, then we'll move on to understanding what is regularization with the help of many simple examples, understanding the working of regularization and various techniques involved in regularization, that is L1 and L2, followed by a hands-on. But before we get started, make sure you subscribe to Edureka's YouTube channel and hit the bell icon to never miss an update. Also, if you're interested in online training certification, do check out the link given in the description. So now let's move on to understanding the need for regularization. So let's take an example here. Suppose you're hungry and you ordered a burger from a nearby burger store. The burger was yummy. But what happened after consuming the burger was that you got food poisoning and you were admitted to the hospital. What happens next? Well, one fine day, your friend wants to take you to McDonald's to give you a treat. You soon recall the past experience of eating a burger and you say, no, eating any burger leads to food poisoning. Well, that is overgeneralization. Just because of one bad incident, you take all other incidences in the same way. Now let us apply this case in machine learning. Suppose we built a machine learning model and wherein if we input a singular noun, the model should predict or give us the plural nouns for any word. Now let's say our training example is bottle. The plural noun is bottles, and another training example is cup. So the prediction is cups, pencil, and the prediction is pencils. Okay. Now we train the model with such words and it learns the pattern that S needs to be added at the end of every word. Now let's give it a model a new input like window. So the prediction the model gives is windows, right? Desk, another input, and the prediction is desk. This is amazing and that is what we wanted. But there is a problem. The model fails to predict the plural nouns for the words like box. The model predict BOXS, but we know that the plural noun for box is boxes, right? Similarly, for men, the model predicts mans, but it is men. We know the actual plural noun of men. And similarly, for leaf, the model predicts leaves, but the plural form is leaves. Machines also falls into the same trap if we are not careful, and this is overgeneralization. And this is also called overfitting in machine learning. That means the models perform well on the training data, but it does not generalize well on the unknown data. The new input here in our case was box, men, and leaf, and here the model is not generalizing well on these data. So this is an overfit model. So you might be thinking as how to overcome the overfitting to make a good model that generalizes well. Well, to answer this question, we have regularization that overcomes the problem of overfitting. So now let's understand what is regularization. So let's take another example of house price prediction, where based on the size of the house, we want to predict the prices. And generally, as the size of the house increases, the prices will also increase. Now, we will have a distribution like this, and we built a linear regression model, and the equation of this looks like this. The prices of the house equals to B0 plus B1x. Now, here B0 and B1 are constant, and this is just a simple linear equation. What we notice here is that if the line is not able to properly fit all the data points and it finds a best fit in terms of a straight line, but we notice that all these data points are away from the line, and also we see the red dots, the test data is here, then this is not a good representation of our data. What do? Well, we built a distribution that looks something like this, right? So we are trying to draw a line that exactly passes through all the data points, and in that case our equation looks like this. Now this is a higher order polynomial equation where we are trying to find out the price of a house based on the size of the house. The issue is that this equation is complex and the line is very curvy, passing through all data points and trying to learn each and every data point. And if you have some unknown data here, then this model will again not be able to generalize the data well. Again, there's a problem, right? So what do? Again, what about this line? Well, this line is a balance between the other two cases that we have just seen. And the equation of this looks something like price is equals to B0 plus B1 into size plus B2 into size square. And this is a less complex equation than the previous one, and the line looks like a curve and it generalizes the data well. So when we have the test data, the equation will give more accurate predictions than the previous ones. Now here the first case is called underfitting The second case is known as overfitting, where the model tries to learn each and every data point. And the third case is called the good fit. The good fit model is a balance between the overfit and underfit model. This good fit model generalizes well on the test data. The model does not try to learn each and every data point. So now how do we get this good fit model and save our model from overfitting? Well, for this, let us understand the working of regularization. Now, here is our overfit line and the equation of the line, right? Now, if we somehow make beta 3 and beta 4 close to 0, then our equation would look something like this. And this becomes a more simple equation, a simple representation of our data. When we are trying to do this, we are trying to reduce the coefficients or shrink the parameters of this equation very close to 0 to get this model and a simple equation for prediction. And the model is known as the regularized model. So now you must be thinking about how do you reduce these coefficients or these parameters. So for this, we use the equation of the cost function or the mean square error, which is given by 1 upon n sigma I equals to 1 till n yi minus yi predicted the whole square. Wondering how do we got this equation? Well, let us understand this quickly. So the size of the house is on x-axis and the prices are on y-axis. And these are our training data, and the line is our model. Actual price of the first data point is this, the red dot, and the predicted price of the first data point is this, which happens to fall on the line. Now the distance between the actual and the predicted value, it's called the error term, denoted by E. Now the error term is given by y actual minus y predicted. Now similarly, the error term for the first point, how do we calculate it? We write it as E1 equals to y1 actual minus y1 predicted. And it goes on up till the nth point in a data set. Like it is given by the nth point is given by En equals to yn actual minus yn predicted. So now we square these error terms to reduce the impact of the negative signs. Thus we get the MSC or the cost function as 1 upon n sigma I equals to 1 till n yi actual minus y predicted the whole square. That is summation of all the error points and doing the average of it. This gives us the mean square error. Now this can also be written as 1 upon n sigma equals to 1 till n by actual minus bjxi the whole square. And here bjxi equals to b0 plus b1 x1 plus b2 into x2 the whole square plus b3 into x3 the whole square. And this is a higher order polynomial equation. And our aim is to reduce the MSC or the error value. And for this, we use different regularization techniques like Ridge and Lasso, that is L2 and L1 techniques. Thus, we are using these regularization techniques to not only reduce the overfitting, but also help our model to generalize well. So now let us understand these various regularization techniques. So basically, we have got two major, most generally used regularization techniques, that is Ridge or L2 regularization and Lasso, which is also known as L1 regularization. So now let's understand the Ridge or L2 regularization. So in statistics, it is called L2 norm or L2 regularization, but we generally call it in machine learning as ridge regression or ridge regularization. So now we have this mean square error or the loss equation, and which is denoted by again the same equation. So we add here another parameter to this equation, that is lambda sigma j equals to 1 till p bj the whole square. Now this is a small bias that we add to our equation, and this is known as the penalty term, which regularizes the coefficients. So I can call this lambda as the tuning parameter, and we add lambda or this penalty to reduce the coefficients and make them really small. And when the coefficients are small, we get a very less complex equation and thus a more generalized model. And in ridge regularization, the lambda penalty is equal to the square of the coefficients. And what happens in lasso regularization is, again, we work with the same loss equation. And now let me tell you one interesting fact here. Lasso has a big name, and it is also known as least absolute shrinkage and selection operator. So it is also used for feature selection, and this reduces the coefficient to 0. So that is why it has got a name as Lasso. So okay, now coming back to the equation. So now we add one penalty again, but the only difference is that instead of squaring the coefficient, we take the absolute value and multiply it with lambda. That is our penalty. We see here that now again the penalty term regularizes the coefficient. And the equation is given by sigma I equals to 1 till n yi minus yi hat, that is yi predicted, plus lambda, and it goes and takes the absolute sum of all the coefficients. and lambda is again a tuning parameter. The similarity between Ridge and Lasso is that they add penalty to the coefficients, but the difference is that Ridge square the coefficients, but Lasso takes the absolute value of the coefficient and multiply it with the penalty, that is lambda. Thus, with Ridge and Lasso, that is L2 and L1 regularizations, we reduce the coefficients and make our equations really simple, which give us a simple representation of the model that is able to generalize well on the unseen or unknown data. Now you must be getting one obvious question, that where to apply which regularization technique, right? So Ridge regularization or L2 regularization is used when we have a lot of features in that data set and all these features have small coefficients, while Lasso or L1 regularization is used when we have small number of features in our data set and few features have high coefficient values. So moving on to our hands-on in Python. So now let's start our hands-on and we'll be using Jupyter Notebook and coding in Python. So we'll start with loading basic libraries, that is pandas, numpy, matplotlib and seaborn for the visualization. And we'll also import some machine learning libraries for importing the linear regression, Ridge, Lasso and R2 square for matrices. Then we will read this CSV file. So this data is taken from the UCI machine repository, that is the auto MPG data set. And our goal is to predict the fuel efficiency, right? So this is a linear regression problem. So since the data is loading, we can see here this asterisk sign. The data is getting loaded. Okay, it's got loaded and we can see the data. It has got some 398 rows and 9 columns. And let's check the information. So information gives us the non-null count, the data type and the columns. So we've got this MPG. This is the miles per gallon of the cars, the cylinder, displacement, horsepower, weight, acceleration, model year, origin and car name. These are the columns that we have in our data. And MPG is the target or the dependent variable which has to be predicted, right? So what will be the fuel efficiency of the car given all these features, right? So we've got some data type also, that these are in floats. We've got 2 object data types. So we'll see how do we convert them also. Now let us just check the null values, and this is being checked by data.isNull.sum because we have stored our data frame or this file in data object here, right? So we see here that we do not get any null values. It's showing 0. But I'll show you something very interesting. When you're doing the data cleaning, especially with the horsepower, what we do is here we give horsepower and we write here .string.isDigit and we get these question marks. Can you see these question marks here? So this is an abnormality in the data which has to be cleaned, right? So what we do is we clean this and we replace this question mark with NaN. Right, so just let's replace them, and now let us see this null value, and now it gives the horsepower as 6, rest all the null values are 0. So now since we have 6 null values, we have to again replace it or fill it. So we fill it with the median, and that's what we are doing here. I fill it, the horsepower has been filled with the median value of the horsepower, and now we check the null values. This is 0. We are doing all these things just to make our data clean, to be ready to be fit to the linear regression model. Now we check the data types. Coming to the data types, since we have 2 object type and we cannot give the object data type to the algorithm because it understands numbers, so we have to convert it into numbers. So this horsepower is converted into float, right? And I just wanted to show you the distribution of various features, how it looks. So let's have a general distribution. So this is the warning which they are giving. We can ignore it, of course, but let's see. It is plotted. Okay, so you can see the distribution of cylinders, and majorly we have got 4 to 5 cylinders car here, and the displacement, as you can see here, it is between like less than 100 to more than 150 or so. Majorly it lies here. Similarly, we can also interpret the spread or the distribution of horsepower here. It ranges, the majorly it lies between the value here, I can say 60 to maybe greater than 100. This is how we can just map the distribution. You can see the acceleration, how beautifully this is normally distributed, and so on. So this was all about the histogram and the KDE plotting. And now let us just see the correlation. This is the statistical description of the correlation of various features. So the diagonal we will always see this will be 1 because this is like MPG with MPG. So let's see the correlation of the target, that is miles per gallon, with cylinders. It is minus 0.77. With displacement, it is minus 0.80. So what does this mean? That it is having strong negative correlation with these cylinders and miles per gallon. And the weight here also is negatively correlated with the target variable, whereas these are weakly correlated, okay? The origin and model year. So even if we ignore it in a model, that will not make much difference. So this is just our inference. We are just looking at the data and inferring these things. But now let us give it to the model. So before that, we will have to pre-process this data. So for pre-processing, we have to drop certain columns, like car name is not necessary. We'll just drop it. And let's just see the first 5 values after dropping it. And this is what we get. So we can also always check here the data.shape, which will tell us how many rows and columns do we have here. So we can always see that we have 398 rows and 8 columns because we've dropped 1, right? Okay, so now let us just separate the independent and dependent features. So that is what we are doing. We are just dropping the target variable and storing all the values in X, and we are just taking the MPG, that is a target variable, storing it in Y. Just making a copy of it. And now from sklearn, we will do the pre-processing. Just we will perform some standardization so that we get these data points. And now we will be scaling our data. And for this, we will be importing pre-processing from sklearn. So after having scaled it, we will do some train test split, just split our data set. And the test size is 30 and the training size is 70. That is a standard, and random state is just 1. So let's just print the test and train shape, and we get here X train is 278 and 7, X test is 120 and 7. So we can see here that 30% is being reserved as the test data and 70% is that training data. Similarly, the shape, we can see the rows and columns of Y train, that is 278 and 1 column, and in Y test we have got 120 rows and 1 column. So we will be testing the results on this X test and Y test. Now let's build the linear regression model. First, we will see the linear regression model, its accuracy, and then we will train it on Lasso and Ridge. So for linear regression model, let's just import this linear regression and fit this model of X train and Y train. And here what we are doing is we are just printing the coefficients of various columns. So in the format of the coefficient for cylinder, and then it prints the coefficient. So the purpose of printing the coefficient is that we will compare these coefficients with our next models of Lasso and Ridge. So here we get it as minus 0.085. For the displacement, the coefficient is 0.304 and so on, right? So these are the small coefficients, so the model will not be that complex. And now we will find the intercept. So the intercept of the model is 0.012. So these are the two things that were important, that is finding out the coefficients and also the intercept. And now let's come to ridge regression, wherein we will fit this ridge and we will provide a value alpha. Here we are giving a small value like the penalty value, and the ridge fit will be X train and Y train. Let's fit it and then print the coefficients. So while we print it, just observe the first coefficient. The ridge coefficient for cylinder is minus 0.080. And here for linear regression, it is minus 0.085. There is not much difference. The coefficient has been reduced, but it has been reduced very little, right? Here it was 0.085, here it is 0.080. And similarly for displacement also, there's just a little change. So, and as we have also learned that this ridge regression is just an extension of linear regression, and so we are just finding very minute difference with the coefficient values here, so they are not being penalized much. That's a good thing. So not much difference with the values. Let's see what Lasso does. So again, we are fitting this Lasso is equals to Lasso alpha, and we have taken alpha as again 0.1, and again we have fitted the X train and Y train. So let's train this model with Lasso, and this is the coefficients that we get. And we have seen that Lasso reduces most of the coefficients to 0. So you can see cylinder, displacement, acceleration, these 3 columns have been reduced to 0. That means they are not needed by the model, and this is why Lasso is also used for feature selection. So it selects horsepower, weight, model year, and origin as the features, right? So Lasso will build the model based on these features and will ignore these coefficients, these features, because its score is 0. They have been reduced to 0. So now let's compare the score. So we will print the regression model score of X train, Y train, and also X test, Y test. So on X train, it gives me, let me hide this first. So on X train, it gives me 0.80. That means the accuracy is 80%. And on training data, it is 84%. That is good. Now let's let's compare the score of the Ridge score. What is it? Again, it is giving me somewhat the same accuracy, 80% and 84% on the training set. So we don't have much difference. It is almost the same because model was not that complex. It was simple. And when we perform the lasso, when we just compare the score of it, we get the training score as 0.78, and that means 78%, and the testing score is 82%. So we see a drop in lasso because it is naturally not selecting all the columns. It is working only with 4 columns and building the model. So we are getting a low score with lasso. So this is how we compare the results with linear regression and its improvement over Ridge and Lasso. Since this was a simple data set, we did not see much of the improvements in the results. But if we are working on a complex data set where we have got a lot of features and a lot of rows, then Ridge and Lasso will definitely give good accuracy and results. So this was the comparison of regularization, Ridge and Lasso techniques. And I hope you've understood this. And that's it from my side. Thank you.
I hope you have enjoyed listening to this video. Please be kind enough to like it, and you can comment any of your doubts and queries, and we will reply them at the earliest. Do look out for more videos in our playlist and subscribe to Edureka channel to learn more. Happy learning!